Oh, hello all.
Hey.
I'm Harish. I'm a consultant developer working at ThoughtWorks, and in here I'm having Praveen Kumar. He's senior consultant at ThoughtWorks. So here we are here to present about building the mobile robot and how we can extend the features in order to make it a futuristic personal assistant. So before that, I would like to know the audience here. How many of you have heard about the mobile robot or worked under the mobile robots, the perception stack, and all those?
Cool.
Cool. Sure. So no worries. Through this talk, we will give you an the overall workflow, how a basic mobile robot is being built, how you can achieve autonomous navigation inside a particular space, and what are the different domains that you need to cover in order to achieve it. So okay, what do we call by building a mobile robot? So as you can see here, we need some kind of hardware, right? So mobile robot is something that hardware that moves inside autonomously. So we need some processing power. We need some sensors to it. So all these, sensors is being incorporated into a particular enclosure, so that becomes a robot. So there are different domains, or different stages in achieving this autonomous navigation. So starting from this, we need some kind of communicative middleware, so that all these sensors with high throughputs, for example, if you see here, it is depth sensor, LiDAR, and wheel encoders. They have multiple data coming each and every second. So we need a proper way of handling this sensor data, so that we can able to process it, and then we can able to use the information from it. So we need some kind of middleware, and these data will be put into the next domain, where we are kind of fusing multiple sensor data. So this is called as sensor fusion. And then this data is actually put to the next one. So we are trying to extract the required information from the fused data. And that is called as perception. And later, the data which we got, we are trying to put some kind of intelligence to it. So we can achieve the planning, so how the bot moves inside a particular area. So what is the shortest distance? So those come under planning stack. And finally, we need to control the motors in order to achieve the motion. So these are the different domains, the basic domains for a mobile robot to work. Okay, so as I said before, the main, the middleware or the software stack for the communication that we need is ROS. ROS is a robotic operating system. As the name suggests, it is not an entire operating system. It is an XDK on which you can try to build an applications for it. For example, ROS is widely selected because it is an open source. It has a global community. For whatever packages we need, we have all the packages present in the ROS system itself. So it is a multi-platform. It can be worked on iOS, Linux, and other platforms as well. And it's commercial friendly. You just need to can put your code to production without being just informing. So that gives us the commercial friendly guide. And the main thing is, why do we reinvent? For example, if we wanted sensor communication to happen, we no need to again start from scratch. Like we no need to initialize the device driver. We no need to set up the APIs and stuff. So instead, we have this SDK. So we have already everything present in it. We just need to build our own application on top of it, like our intelligence, like what we wanted to achieve as a part of mobile robot. So that's why we go with ROS to shorten the time to market. Okay, so next, this is the overall workflow of a mobile robot. The simple thing that you need to keep in mind here is see, think, and act. So the mobile robot sees what in the environment it is, and it will think how to move, and then it will act. So if you see here, it will actually seeing the real world environment. It perceives the data in the real world, and then with this kind of the algorithm that you will be seeing later. So we are kind of perceiving the environment and then building a kind of map. And with that map, we are able to move and make the path planning. And later, we are executing it. So we will see each and everything in our upcoming slides. So first, let's see the perception. So now you can see there the chessboard. So for us, it might be difficult, but for the computer, it will be easy to know where the chessboard or where each chess, the coins are. Whereas this, if you see this image, if some kind of student or some small children walks in front of an autonomous vehicle or some kind of automated vehicle, we need to tell the vehicle that it needs to stop. So that might be easy for us to stop immediately, but we need to train the vehicle to make it stop. So these stacks come under perception. So the basic perception, only if we have the basic perception stack, we can able to do some kind of simple activities also. So only if we perceive the environment, the bot can move at least one step. So even if we don't know that what is in front of it, we cannot even move the one step also, right? So perception is the very basic stack which is required. So if you see here, these are the multiple sensors available for the perception stack. We can actually select these sensors depending on our requirements. For example, in this kind of exhibition space, there will be multiple crowds running. So we cannot just go with a single sensor. We need to add multiple sensors to it so that we can error correct it and we can able to move the sensor. So for example, in the distance sensors, you have this depth camera, LiDAR, and IR sensor, wheel encoders. So these gives the distance of the object or distance of the robot that it has traveled so far. And if you see some kind of audio-based sensors also, like a microphone, and touch sensor is magnet, Hall effect sensor, and vision is camera, and this is the auto vision camera. So these are the different sensors which is used for perception stack. Okay, so now we are able to get the data from the environment. Now what's next? We need to tell how our bot and where the sensors is being present on the bot. So if you see here, this is a real bot that we tested in our office. So we have actually kind of created the model of the bot in our simulator. So if you see, this is a bot, but it's a black in color. So we need to specify where each sensor is present in the bot. For example, if you see here, the camera is present here, and we have a LiDAR at the bottom. So if you see here, we specify these transforms from the base link of the robot. So there should be some kind of reference link for the robot. So that is we call as base link. So we need to specify where the camera or LiDAR or the wheel encoders from the base link of the robot. So these are called as static transform. So static transform is throughout the journey of the robot, this transform never turns because we know the sensor has been fixed to the bot, so it will not change anywhere. So this is called as static transforms. There is something another called dynamic transforms. So what it does is, so if you see here, these are the sensors which is present in the bot. So this is a static transform from the base link of the robot, whereas there is something called map. So from map to base link, this is called as dynamic transform because while the car moves, the transform also changes. So basically the transform is nothing but it's a distance with orientation. That's it. From one point, in which distance and in which orientation the sensor is present or the car is present. So that is the transform. Okay. So these are the things that you should keep in mind so that the next steps you will get an idea. So how we can achieve the autonomous navigation. So moving on to the next slides. Okay. Now we know we're able to perceive the data in the environment. We know where the obstacle is and whether it's a free space or whether there is obstacle in front of it. And also, we can able to tell the bot that I am this much distance from this particular place because of dynamic transform. So these things are there. So now, the next important thing is we need to create a map. For a mobile robot to move in a particular environment, it doesn't know, right? So where is the restroom or where is the entrance, those things. So we need to create a map so that the bot can use the map and for navigation. So in the process of creating a map, we call it as simultaneous localization and mapping, which is called as SLAM. So if you see here, this is the robot. So whenever it moves, it will automatically generate a map and it can able to save it. So this is example of a 2D map, whereas if you see here, this is example of a 3D map. You can actually kind of recreate the space using 3D SLAM. So why these things and why we are having localization and also mapping is, we need to know, for example, if the bot is here, the data from the sensors on the bot is actually the LiDAR sensor. So throughout the obstacles which is present around the bot, if I'm standing here, it will create an object. For example, that is object. So when the bot is here, it will create a line there. You see, the black lines are the objects and white lines are the open areas. So when the bot moves here, the obstacle will be in left-hand side for me. Whereas the bot is here, obstacle will be right-hand side for me. So this is how the bot knows. Only if it is localizes, the bot knows, okay, whether the obstacle is in the right or in the left. So that's why we are actually simultaneously localizing and generating the map. So there are multiple libraries. So AMCL, which gives the localization by fusing multiple sensors. And we have SLAM toolbox to generate 2D SLAM. And we have RTAB for generating 3D SLAM. So one another example is here. For example, think a vacuum cleaner is inside a room, and this is if the vacuum cleaner is trying to clean the room by a random movement, it can actually go in the place where it already moved, right? So if I'm just giving it as a random movement, I'm going here and I'm cleaning like this, and if I come here, it is just like again coming back to the same place where it has already cleaned. So that's why we are going with localization. So we can able to perceive where the bot is inside a particular room, and we can generate proper path so that it clears the room with a proper manner instead of reiterating or again moving in the same place. So that's why the localization is important while mapping. Okay, next is the important part. Now we have the sensor data, and we know where the sensor is in a particular place, and we have already by the previous thing we have generated a map. So now what? We wanted to do the autonomous navigation. So that's over to you, Praveen.
Hey. Hello. Hey folks. Thank you, Harish. Now that we have the map ready, right? Like till now, we have been using the sensors to understand the environment, right? So what SLAM is doing for us is generating the map, and it's going to give you a 3D or 2D. It's dependent. Like it's dependent on your need, like whether to go for a 3D map or 2D map. Now that if you are doing a simple operation, solving simple problems, you can go with the like a simple 2D map, and which gives you just an occupancy grid. Like occupancy grid simply means it's about the environment, right? So you are defining the environment, whether it is an obstacle or a free space. Like that's what you collected with the sensors in the previous step, right? So simultaneously you did some sensor fusion and collected the data, fused it. You now have the map. Now what's next, right? We are going to navigate the bot. Like for us to say it's an autonomous mobile robot. The basic core functionality of an autonomous bot is just that it has to move somewhere, right? So for if you can imagine, like I want to go into take a mobile robot for example. I mean indoor mobile robot for an example, right? Let's say I want to I'm standing here. I want to go to the entrance of this conference hall. So in that case, what I have a map ready that is already collected from the map. I mean the SLAM phase, and now I have the current pose of my like the bot. Assume we have the current position and we want to give the target position. So with that, what I can ask, right, like take Google Maps for an example. This is what all it needed, right? You have the current pose and you have the you will be giving a target pose, and you already have the map ready. Now you want something to actually find your path, right? Like path is something like it has to be short, it has to be efficient, even it has to be dynamic too, because it has to be dependent on what vehicle you are riding, right? So it has to think about how many how far it is, can I drive a car in that place, can I drive my bike in that place, all those things, right? All those are actually configured, and we can use that with the dynamic mapping. Now we have some components that helps us in this phase, like for example, Global Planner is a model in the phase of navigation, right? So Global Planner helps you to find a path. So if you give a current location and the target location on a map, it's going to compute you the path, and then with that map, what you're going to actually do is you want to drive your vehicle, right? You want to drive your vehicle, you want to move your bot. That's all. So for that, you need another component, which is controller or local planner. Local planner is something like it's going to drive the vehicle. That's all. It's not going to do anything. It has to send the drive commands to the vehicle based on what it sees. Like it has to drive through, and it has to see the obstacles around it, and it has to just send increase the speed, move right, move left. These are all the simple commands that you can give to a bot so that it moves. And then you have this cost map, which is I would say you're adding some additional information, like not just a static map that you collected, because the static map will only have the static information. Let's say it will have informations about the chairs, tables, and other things, all those things. But if there is a dynamic obstacle and you want to actually feel that and have it in your map, so that your pathfinding algorithm is actually computing the correct path, and your bot is actually driving through the path without like hitting anything, or with avoiding obstacles and taking correct path. So these are all the core components that I would say for navigation is like I would say, like, you can think of, if you want to do some navigation, you can clearly use, I mean, you want to use global planner, local planner, and cost maps, right? Let's go to the next slide. Okay, so here if you see, this is a high level workflow of navigation. I would really like to start from the right of it, so where you see like the map server. So map server is nothing but, you already collected the data about your map. So this component, whatever we have been talking, like cost maps, planners, and other things, right? They need those data, and when we are talking about real time, it also the data from your sensors, right? So sensors, like you have various sensors, like depending on the condition, you have LiDAR, depth cameras, range sensors, IR sensors, and other things, right? So you can receive those information from your sensor data, and you can also define some recovery behaviors, but that's not actually covered in depth here. But we can based on the local cost map, local environment. Cost map is nothing but it's just a enhanced map, I would say, right? So you have some dynamic information about the real time, and you add it, and you also have a global cost map that adds additional information about your map, the whole whole map that you generated in the SLAM. So if you see, the flow is actually coming from the right. It's going, you are creating a cost map, and the cost map is fed into the global planner and the local planner, right? You have two separate cost maps that will be used by your planners. And then if you see, take a look at local planner. Local planner does nothing but just send some commands to, if you see command velocity. Command velocity is some nothing but you have a data structure that conveys my linear velocity and angular velocity. If you see, you have a controller. Controller is nothing but high level hardware abstraction that takes in the data and conveys that to the hardware, real hardware, because hardware cannot really understand what you're talking in software, right? So you need something called controller, and you get some odometry information for you to actually work on localization and other things. So these are all the things that Harish talked about. Next thing is your map server. So I would really switch the gears and move on. So like map server is nothing but it's a component that serves you the information about the map that you generated in the SLAM. So it just you can think of like you make an API call to the server and get the map information. It's just a plain image, nothing much. It is going to have, if you take a look, this is the simulated environment. It's kind of a puzzle or something, and this is the map that you see. Like this is talking about, if you see, it represents data. I mean, at least the map with these two values. If it is white in color, then it is free space. If it is black in color, then it is obstacle. And there are some other spaces, like if you see here, it's gray in color, which is unknown. Okay, so Bart cannot. It couldn't find the place, so it said it is unknown. And this is what they, if you are really interested in the code part of it, I mean the class diagram and other things, you can actually understand this. You have layers in the cost map, and a cost map is not single file or a class object instance that takes in all the values about your real-time environment. It also collects data in layers. Like you can have n number of layers. You can write plugins on your own to actually separate out the obstacles which matters to you. So for example, you have an obstacle layer. So if you see, obstacle layer is one kind of layer that deals with only 2D obstacles. 2D obstacles is going to have information from the LiDAR, and it's going to collect, okay, these are all my obstacles. And you have static layer. Static layer is nothing but the map server actually gives you some maps, right? So that's your static layer. And then this voxel. Voxel deals with 3D objects. It's the exact same of obstacle layer, but it also handles the 3D information. And here you have inflation layer. It is not dealing with any real data, but it's going to inflate the information, like whatever you get from the obstacles, 3D voxels and other things. It's going to inflate it so that your path planners and the components which consumes this information, like the cost map information, right? So it's going to help you to actually find a better path. Like if you don't inflate a particular object, let's say you have a table here, and if you inflate it, the map is going to maybe I'll switch to the next slide, you can better understand it. So if you see here, you have a static layer here, and then you add your obstacle layers, and you can inflate it. So in the master slide, what you can see is like here you have some obstacles, and here you are having some obstacles, right? And by you inflating something here, so what you are really doing is you are expanding the difficulties. Like if you just say if you just feed this information to your planner, then it's going to confuse. Assume that there are free spaces there so that I can take some plan here, but that's not something really you want, right? So you want your bot to be safe, and you want to drive your vehicle safely, right? So you want to inflate your information so that your bot at least avoids crossing the obstacle by like little, maybe it's not going to go very close to it. So that's the idea. So you have different layers, and that's what I was talking about. You can read it. And the next thing, so what is something, I mean, we talked about global planners, right? So you have the information that is available in your cost map and other things, but now you want to find the path, right? Like there are algorithms that finds you a path in a in an efficient manner. A star is one of them. It's actually often used in robotics, and it's in like it can be used in combination with some steering models, like your car is going to have a different steering model, and some other bots like differential drives and other vehicles are there that has different steering models. So you can use so you can use Dubin's or Rechip motion planners for that, for different steering nature. So you have many algorithms available there. You can actually explore that. Next is actually, this is what you actually see. This is a simulated robot. It's a differential drive bot, and you have this pink color path, which is the global path that's generated for a particular target location. And this is your local planner generating a path for a lesser size, lesser area. It's not going to compute the local path for a complete environment, and it's just covering, let's say, if it is a differential drive bot of size, let's say 1 feet to 1 feet, then it's going to cover 4 meters. Then it's not going to create a plan for the entire global plan that was generated. It's going to consider only small amount of area, and it's going to navigate in that place. So yeah, local planners. So as we already talked about, this is just taking the information from your the cost map, and it's going to drive the vehicle, right? So it's just taking the cost map and doing some basic obstacle avoidance, creating a local plan, and drive your vehicle, send drive commands to your vehicle. So that's what sorry for that's my bad. So you have your local planner component here, and that just sends command velocity, which is nothing but linear and angular velocity, okay? And you have many algorithms to do all these tasks. So DWA, TEB, pure pursuit are some often used algorithms. DWA is like a better algorithm because if you use a complex area, then DWA will be a good option for you. And ROS control. ROS control, as I already talked about, it's going to deal with the hardware part of it, hardware abstraction layer, right? So you have some hardware, you have some software. Now you want to connect them both. Let's say software says I want to move right or move straight for 5 meters. So in that case, what's going to happen is like your controller is actually going to take the data in and convert that, and it's going to actually send some drive commands. Like assume it's in hardware level drive command, okay? Like motor speed, actuator speed, and other things. Like you have different drive bots here. This is an omnidirectional drive which can drive in any direction. This is an Ackermann steering. So Ackermann is a car steering. Like you are using your car, right? So your car cannot really move on any direction at that same time. So you need some steering nature that needs to be fitted into the board. Sorry, the controller. So that takes in and the mission control. So we now have all the components ready, right? So you can drive your bot, you can navigate in a bot, you can perceive the environment, all the things are ready. Now comes to the mission, right? So without a mission, you cannot, like you have your bot with the software components that can take tasks. Unless you give them some task, it cannot really do, right? So take this forklift or fork for an example, right? So it has to do some tasks repetitively, right? It has to receive some commands from somewhere like, okay, if you're here, go and collect something from there, and put it somewhere. These are all some simple missions or tasks that you can think of, and you can really feed them with this trees. Like behavior tree is one another stack, or a way of actually implementing it. Behavior tree is a separate concept, and it is used in gaming and other things. It is also used in kind of repetitive tasks, like your cleaner bot has some repetitive tasks to do, right? It all composed to you can decompose every task into smaller child tasks, and you can repeat the same, right? You can add recovery behaviors and other things. Now that we have had all the things, I would like to get Harish back and talk about simulation and other things.
Yeah, thanks Praveen. So okay, so we know we have all the software stack ready. Before going to buy the hardware, we should get some kind of confidence that our code works properly. So then we can go and buy hardware, we can start working on it. That's how the simulation comes in. So we can actually test the full control and the full algorithm what we have generated in a simulation. So we are from autonomous vehicles domain. There are multiple AV simulators in market, but one for the indoor robot, so which is 1/10 of the autonomous vehicles which is running in the outside. So we have a simulator called Gazebo. It's an open source. We can actually we have actually used it. So if you see here, this is the real bot that I showed you before of what we have done in the simulator environment. Simulator is just nothing but a physics engine. So we need to specify the inertia, mass of our design, so that it will give how it will react in the real world. So kind of near to the real world. So you can see here, when I give the goalpost here, the bot autonomously generates the path through the algorithms that Praveen was telling, and we can perceive the data, what are the obstacles around. If you see here, these are the obstacles around it, and then it generates a path so that it doesn't hit and it reaches to the destination. So these are the inflation rays like that Praveen was telling, so that it takes a kind of smoother path so that the bot will be safer. It doesn't hit to the obstacles. So this is the full-fledged the simulation data of what we have talked before. We can able to use the simulation in our CI pipeline also. So whatever the algorithm that we tweak, whatever the changes that we do, it will be tested as a part of the pipeline. So we can cut down the time to road, and we can able to quickly develop on it. So moving on to the personal assistant features, we are currently exploring the Flutter for embedded. So we can have some kind of kiosk on the bot so that we can try to interact with it. So see, for a personal assistant, you need some kind of interaction, and the data should be something we need to hear from it. So we are trying to explore Flutter. Why? Because it is a multi-platform. You can have a single code base, and you can try to run on Linux, Windows, and Android, all these things. So we are currently building Flutter for embedded, so we can just directly run on a low-level embedded controllers. So we are trying to integrate the speech recognition, the motion tracking, so we can try to increase the features of the mobile robot to make it more like a personal assistant. And there are other applications as well.
You talk about it.
Yeah, so one of the applications is like education. So we can try to build some kind of education coding practices to the people, and it can act as like buddy, and this can act as actual surveillance because we have already sensors, cameras present in it. We just need to get the data, need to publish to some kind of some cloud, and we can able to get the data, and we can able to see like a surveillance when there is no one in the home. And we can use it like a medical assistant, which reminds you to take some kind of medicines and etc. So these are the simple applications that we could think of. And we have some kind of challenges. For example, in hardware, so processing power is the main thing. So currently we have multiple sensors, especially we are going for a camera-based depth one. We need a kind of GPU to convert the perception data, that is the camera data, visual data, into a point cloud, so that we know exactly the 3D data is. So the processing power is a main thing there. So if we have some kind of GPU, then it will be easy. We can just processing on the edge itself. Otherwise, we need to have some kind of server where we need to do processing on the server, and we just need to send the command velocity data to the robot to do the things. And the sensor noise, yeah, because there are multiple sensors, we need to make sure that we don't have noise and we don't have errors because of it. And battery backup, connectivity, and the software challenges. Yeah.
And actually, in the sensor noise part, it's actually dependent, right? If you use quality sensors and if you use quality algorithms to actually fuse the data, it's not going to like really affect you. But it also depends, because the connections and the environment can actually add in some noise to the data. So your algorithm has to be very dynamic and effective to actually understand the data and fuse it, so that you make something out of it and you actually can use it. And the software challenges, yeah, of course, the sensor data processing. Your algorithm has to be very like it has to be very efficient first of all, right? So because you are dealing with bunch of, it is not simple data, right? Like when you talk about 3D lidars and depth cameras, it is huge data, and if you talk about the frames per second, it will be on 120, 130 frames per second, and you're dealing with this, and your algorithm has to be very efficient and reliable, because your algorithm should never fail. And that it also has some things like odom drift, because we are actually measuring the distance traveled with this odometry sensors that actually in the board, and the noise reduction, because we are actually using all the sensors and other things, right? So your data processing and the algorithm has to be very reliable and effective. And perception, because perception is a really huge problem to solve. We are solving very regular problems like you can navigate inside a door or something, but the road, if you talk about real roads and different circumstances, and maybe different weather conditions, it will be really worse. So perception is really hard, and localization in the same. It's going to you need to really work on it. So these are all some software challenges that we would like to add. Yep. QA, any questions?
Yeah.
Myself Shobhan. I'm working in industrial automation for the last 25 years. So since it is IoT is emerging in the recent years, so
can you be a bit louder?
Yeah. So here, so far we discussed about this mobile robot, right? The actuation is based on the wheels, right? So wheel is rotating, and then we move front and backward and all these things. What about the walking robots? So what complexity it adds to this? I mean, something like a reinforcement learning. What's your experience in this?
It's really about the different controllers that we use, because it's if you talk about the controllers that deals with the data, it really doesn't matter, like until your local planner actually sends the correct commands, right? And your bot and the controller can actually, if it is a standing bot, it has to deal with the gravity and other things too, right? It has to deal with the walking motion and other things. All these things are actually can be embedded in the controller, and your bot majority of the work can be solved in the controller level too. And your application stack, like your software stack can just deal with motion planning and other things. Like you can, like it's actually the responsibility principle, right? So who's responsible for what, right? Like controller can be responsible for handling most of the logics, like that really depends, right? Like how you want to deal with the things. Like if it is a standing or legged robot, then most of the things, yeah, as I told you, like it can be handled the control level.
For example, the inverted pendulum.
Yeah.
You would have heard about, right? It has only 2 wheels, and the most of the weight is vertical.
Yep.
So there is a chance that always it's moving front and back like this when it is moving. So that time we have to control both the wheels, so that the robot is always in a steady position. Yep. So that's a quite challenging task.
That's an interesting question, right? So you really have to deal with
complexity. Increases when we have the robots from moving robot. I mean from wheels to walking robots.
And the same complexity to aerial bots and other things. Like they have their own complexity.
The
and
classical example is the Boston Dynamics. You would have heard about the dog robots and all these things.
Yep.
So what's the gap, the skill set or the complexity increases when we go from the mobile robots like a wheel robots to the walking robots, or the actually dog robot, something like that.
Yep. So I'd like to take that. So we at ThoughtWorks, we really are not solving these kind of problems. We are service companies, and we are actually we can actually hire some researchers to do all these things, right? So researchers are some people like they read about all these things, work with gravity, they design the model, right? So if it is a leg robot, what should be my velocity? If it is a different problem altogether, how I want to resolve it. So all these things are actually solved in your control again. So you need to hire some researchers and get them. You cannot really do the work with the software developers, because they know how to write drivers and other things, but research things, yeah, of course, like you need to have some PhD.
You mean the mathematical modeling?
Mathematical modeling
The
and
AI part
physicals
of,
and
yeah,
other
the
things.
data set. Actually, I am from Autonomous Vehicles Initiative team. So where we have a separate data team which works on RL model, generating RL model for a car on a road. So we are using car law simulator. Using the car law simulator, we are generating a model in order to make the car move in a straight line. So we are actually having a separate data team. So I think they might help us for this creating the RL model for the legged robot. So we can actually try to solve it through the simulators first, and then we can go for the real hardware and we can go on it.
And yeah, kind of reinforcement model is like how you solve the problem, right? Before that, even you actually need to model your bot, right? Modeling the bot is really the other part, like the controller part. So how your bot is receiving the hardware or creating the hardware abstraction layer. Hardware abstraction layer is something, you know, that can be, you know, like grouped into the or embedded into the device itself, right? So you you write the device drivers, you write controllers and other things. You just move it or deploy it in the bot, and you just send the actual application commands to the bot, right? That's what you really worried, and like in the architecture part of it, right? So architecture only talks about, like, you know, you have to have you know, a decent responsibility, you know, like chain, right? So you cannot you know, like overload a particular application stack. But you know, if you really need something is needed, then you need to create another level of abstraction and use it with your application stack. That really, you know, differs. And if you want to really work on, you know, some research things, then you really need to work on researching people. Yeah.
Thank you.
Yeah.
Yes.
Sorry, just the processor part which you were speaking about, is it like an ARM-based processor you use to create the design maps and everything?
It really depends, because the processing unit, the power that you get, right? Like currently GPUs are the, you know, like interesting or you know, challenging part. Hari, would you like to
we are using a single board computer, the Raspberry Pi, for, you know, to fetch the data and send the data to a particular you know, laptop, and we are doing all the processing on the our host machine which we have in the hand. So we are not doing processing on the edge. So we are actually having the in the part of pipeline. So to make the processing power on the edge by having more, you know, tegra processors and like kind of high you know, throughput based processors.
Okay. Is serverless is an option? Like we have services like Lambda and cloud, right? Is it an option, like if we have low latency, we can do a high processing, get it back? Because you said processor is a limitation, right?
Yeah, so it depends. Like as you said, the communication differs. Like if we are, you know, trying to, we actually worked on a problem where it is an exhibition space like this. So at the time, the connectivity is very difficult for the bot to take care. So and also the data that it takes, for example, the 3D lidar, it takes huge amount of data which needs to be transmitted, and the algorithm should be done, and then again should send the data. So those, when we have huge amount of data, it will be difficult for that to, you know, communicate with the hardware limitations that we have.
And just an add on there, like, you know, you can solve that problem with, you know, effective Wi-Fi router and other things, right? Like RAS is already providing the communication stack. You just need to have some, you know, like physical communication, right? That's all.
Last question. The software part of it, do you use like C language for using the algorithm, or
Any system programming language. Currently, we are using C++ and Rust.
Yeah.
Rust?
So
At ThoughtWorks, we are proposing the modern programming language. Harish can talk about it better. Rust.
Yeah, so we are actually exploring the Rust. So in order we try to replace C++ with Rust. So wherever we have Rust, we're trying to you know, replace with C++. We are replacing with Rust, and the ROS supports C++ for now. With currently the ROS based Rust is currently you know, kindly developing. We are actually trying to integrate it, and we're trying to contribute to the open source also. And we have Python also. So according to ROS, is supported as Python and C++. We are exploring the Rust part as well.
Thank you.
So yeah, personally me, I like C++. So
Hello.
I just handed over the question to him.
How you are transferring this video streaming, I mean, from the edge, I mean, the robot to the central station?
So currently we are you know, doing communication on the computer only. So we are using the router, separate router for it. We are trying to, you know, get the data to that instead of using in the corporate Wi-Fi. So we actually solved in that way, because only with 5 gigahertz Wi-Fi band we can able to transmit heavy data. But when we are trying to go away from the router, it is kind of dropping few data because of heavy load. So that's why we had, you know, incorporated a separate router for it without internet, and so we had a local network for it for communication. So we are trying to, you know, so like, you know, because of Raspberry Pi, it doesn't have that much signal, you know, the strength, especially the 5 gigahertz band. We went with a LAN cable. We just had a separate router for on the bot itself, and we communicate through that. So I think you can see in the so yeah, here we have our separate router, and we actually kind of did data transmit over that. So we have in future thought of having plans to increase the processor to do all the processing on the board itself instead of transferring to the particular server. We can actually
Okay, thank you.
So if you want to migrate that processing into the robot itself, so what kind of hardware you are evaluating? Are you exploring some hardware for that? Or?
Yeah, so we are exploring the hardware. So we have plans to incorporate Tegra process and see how the performance differences. So currently we are having that kind of research in the pipeline. So we are kind of exploring that.
So do you have some vendors or some products in mind so that we can also explore that?
Not yet. Like we are exploring on that as well. So we are looking for some kind of GPU-based, the single board computers to incorporate into the board that we have.
So, okay. One more question about localization. So initially you are doing that mapping of the. Let's take this auditorium also. So initially you'll be doing the mapping with the help of the robot. So after that, for positioning, are you using any like RTLS, like BLE-based indoor positioning or something to locate the bot, or how will you locate that? If it is
I didn't quite get the question. Like, what is it? RTL?
Yeah, if it is outside environment, we will get a GPS to locate the position of the bot.
Yep.
So inside this, you will not get the GPS. So is it dependent on the indoor positioning, any kind of indoor positioning, like to locate the bot initially?
Yeah, so currently we don't have some kind of third-party sensors. For example, the Bluetooth beacons that we have part of our pipeline to aid the Bluetooth beacons-based indoor navigation. But currently we are using the localization using the perception stack.
Perception work. Okay, but let's assume that robot is somewhere. But initially, how will you know it is there?
Yeah. So that is that's something called state estimation. So actually, we thought of covering it, but it will take a lot of time. So state estimation is what we need to tell the bot initially. So the initial portion needs to be given manually. For example, in our case, we had something called dock to charge it. So we always set to the dock, and we set the state estimation because we know manually that where the dock is. So that gives us the hard-coded value for the state estimation, and whenever the bot is on the dock, it is state estimated and it started its journey. And after that, it doesn't require, it will keep on localizing itself and able to localize itself inside a map. So the initial part is that manually we need to set. That is called state estimation.
But let's assume it has moved from the initial state and
Post
it is
estimation.
somewhere.
Yeah.
Post estimation.
Yes, it is now moved to some other place, but how will you know from it is at that some other place or where it is located?
Yeah, so immediately it can't able to localize. It needs to move a little bit so that it perceives a new environment, and it will try to localize with the map that is already it has. And then it will automatically move to that particular place.
And you also have this odometry sensor, right? Like odometry sensor is going to tell you how far it is actually moved from the origin, right? Like you can actually compute the data, and state
so
estimation
you are
comes
using
to
the
this.
acceleration and the distance.
That is from IMU. But even if we take the bot and keep it in some new place, when the bot moves a certain distance from the environment, from the map, it can able to localize itself in the new position.
And you also have some sensors, right? Like IMUs, GPS. You can fuse all this information to get the actual position.
So
like
does this 2D map or 3D map you are generating has a unique number for a particular position, or how it will?
Yeah. So So as he said, like the cost map. So on the cost map, we have the X, Y, Z coordinates, and that what tells the bot where it is currently positioned. So especially the one that I was telling, if we take the bot and keep it there with the 2D map, it will find it difficult to localize it. But if we have some kind of 3D based data, that as I saw 3D SLAM, so in that case, it can able to localize because it has multiple characteristics. For example, from the wall, the fan, and the top, it can able to use multiple characteristics to localize itself. But if it is 2D map, it will be just a line, and it will be just a box. It will find difficult for it because there will be multiple boxes in the same house, a kind of a room. So it will find it difficult. So if you go with the 3D based one, it can able to localize itself better.
And that's where the cost map comes into the picture, and you have 3D layers which defines the objects in the runtime.
So for example, simple example is autonomous vehicles. We have multiple LiDARs. So why? Just because safety. We have multiple LiDARs to we fuse it. Even though one LiDAR is enough, we are fusing multiple LiDARs and to get the proper environment so that it can able to move.
So do you think there could be still some error in localization with this method, or?
Sorry?
Still there could be some possibility of errors in localization with this like 2D or 3D map?
Yeah, I mean that can be actually avoided because you are fusing multiple sensors, not just sliders. Right? So you have many sensors, and it's not that very accurate,
Yeah,
but you
that is
still
the
have
probability that
you know,
two
still-
different locations.
Yeah, it's actually
can have the
probability.
same
Yeah,
Right
exactly.
now we are working on probability based algorithms, right? Like if you really go for deep learning algorithms, reinforcements and other things, like you can expect a better result.
So for example, AV itself, we have multiple sensors like the LiDAR, the radar, the IMU, the GPS because it's outside, and we need to input the HD map. Those things. So only if we get kind of incorporate everything, we can able to get the proper localization.
If you have multiple like LiDARs, right, then why does you say like you have a problem with the unstructured data? It automatically can detect it, right?
Unstructured data is like
Environment without the maps, dynamic environments, you are having a problem. You already have a LiDAR, and you say multiple LiDARs are also available.
yeah, it's about fusing the data, right? Like you have the data ready, but you need to effectively fuse it to actually, even though you have your map ready and other things, you have to localize, right? So when you have 100 people in the same room, it is going to have lot of obstacles, and it cannot actually localize itself in the environment because the map information that it is there already is going to confuse the bot, right? Where am I? That would be the question.
But it already knows its location, right? First.
Yeah, so there might be, yeah, that's why. So you're telling location is mean by GPS, is it?
Yeah, like I'm talking from the automotive perspective. I'm trying to tell you why can't we bring that automotive perspective into the indoor navigation? What is stopping? Like, is that a processing power? It cannot process that much data faster, or
Not just the processing power, the errors in it. For example, as Praveen was telling, the ODOM data, when the time passes, it tends to deviate from the original.
cumulative errors.
Yeah, errors will be there. So while while running it for a longer time, so that's why we are aiding with multiple sensors to make it more precise. I mean, increase the localize. Otherwise, it will work, but it might fail at times. Like it might fail. Immediately it goes inside some kind of obstacles. It will fail to localize, and that's why we are aiding with multiple sensors. So for example, we face this error while moving itself. If we just aid the ODOM data, it will try to move inside the obstacles inside the map. So when it goes inside the obstacle, it will go inside the recovery thing and it will stop until someone gets more out of it. Whereas if we add the camera data depth sensor to it, it will know, okay, I am here. Even though the ODOM data is away, I know, okay, from the obstacle it is here. So it will error correct it and it will again come to the proper place. So that's why we are going for multiple sensors.
And one more information is like you can make your bot really intelligent by adding lot of sensors, right? But what is the need? For a mobile robot, will you be like interested in getting all the sensors available and putting into a mobile robot and make it so intelligent, right? That's not actually the real need. You can do it for a car, like it actually deals with different environments. But for a mobile robot, you can keep it little simple. Yeah.
Simpler depending upon the environment.
But you can put necessary things to just get out these difficulties at least.
Sorry.
Like in car, it's real time. It's safety requirement, but in here, it's at least you can pull in necessary sensors to make it work.
We also have the safety sense standards, right? Like the T522 something like.
So we
that
also
has to be obeyed.
Yeah, recently there is a standards been given for the mobile robots as well. If we have all the standards been passed, so that will kind of solve us the problems faced generally from the mobile robot side. And as I said, depending upon the requirements, we can aid the sensors. For example, if industrial automation side, we can able to just add few lines, the line-based guidance, or we can just make it like induction-based guidance instead of making it fully autonomous. So depending upon the environment, we can try to aid the data and we can work on it.